I think more a knowledge sharing.
Yes, sir. Yes, sir. That's what it is, sir.
So I think your chapter has got the acknowledgement. I spoke to head office.
Oh, they given, sir?
எல்லாருக்கும் அனுப்பிட்டாங்க.
Oh, very nice, sir. Thank you, sir. Thank you for swift action. And actually, ரெண்டு மூணு பேர் ரெஸ்பாண்ட் பண்ணிருந்தாங்க, நான் தான் கேட்டோம்.
மெசேஜ் போட்டாங்க, எல்லாருக்கும் அனுப்பிட்டு சார், யாருக்கும் வரலன்னு சொல்லுங்க, நான் அனுப்புறேன்னு சொன்னேன்.
கண்டிப்பா. We'll wait for another. We'll start 2:40, sir. 2:35.
As you say, sir.
Kailesh.
Yes, sir.
We'll start another 2 minutes. 2:35 will start, huh?
Okay, sir. Actually, Mr. Senthil.
Yes, sir. Yes, sir.
There's a lot of metallurgical fundamentals which can be shared.
Yes.
Now, I'm giving you only iron carbon diagram.
Okay.
There's one more before iron carbon, which is fundamentals of metallurgy itself. Then after iron carbon diagram, as Mr. Dayalan was saying, then we go to TTT diagrams.
No. He's given recommendations based on the time availability. You can pick that.
No. I'm just saying, if you have to share knowledge, I would love to share my knowledge. First is what is known as fundamentals of metallurgy. Then there is what I'm going to talk to the iron carbon diagram.
Okay.
Then after this, you have what is known as the TTT diagrams.
Oh, very nice. Okay.
These three, if our interested members are interested, this gives them a total holistic view of total iron metallurgy. Similarly, you have non-ferrous also on aluminum and copper. There are also a lot of exciting fields are there.
Oh, yes, sir. Sir, if you can do further one also, I'll be happy, sir. Based on your time.
I'd love to know. There are two things here, Senthil. You'll appreciate what I'm saying. I'm running my own business. And this is my passion. And both the times, it's very conflicting, you know. In fact, I just returned today morning at 3 o'clock from Pune by car.
Same, sir. We understand. I'm also in the same blood.
And when we take up this responsibility, we have to do a good job.
Yes. So that's what it is. That is why I took your time, because I know how difficult it is, but still I had to thank you because you could allocate some time.
Sir, 36 people have come. Shall we start?
Kailesh?
Sir, yes, sir.
Yeah, can we start?
Yes, sir, we can start, sir.
Okay.
Sir, we can start. 36 is a good start. Ravi Chandramouli garu.
చెప్పండి రా రెడ్డి గారు,
నమస్కారం బాగున్నారా?
దేవుడి దయవల్ల మీ దయవల్ల బాగున్నాం.
We are all proud of you. You are very sincere and hard working guy.
No, we are all like that, sir. All of us. I know how much monthly you travel. I know India abroad, Gudur, Hyderabad, Jamnagar. I know you.
But I cannot travel at your age, you know. That is the difference. Your age, see how you are traveling.
When you reach my age, you'll be traveling in a helicopter, Reddy garu.
No. I want to be at home.
Senthil sir.
சொல்லுங்க ராஜ்.
சார் கேக்குற மாதிரி ஸ்டார்ட் பண்ணிடலாமா?
ஸ்டார்ட் பண்ணுங்க.
Good afternoon, everyone. Warm welcome actually to today's webinar. I request our chairman, Mr. Senthil Kumar, to do the welcome address.
Good afternoon, fellow Foundrymen. On behalf of Indian Institute of Foundrymen Chennai chapter, it gives me great pleasure to welcome you all for this technical webinar along with the Hyderabad chapter. And we are delighted to have your presence. Generally, allocating time is the biggest challenge. And I understand that you people have joined here to enrich your knowledge. Thank you for the same. Today's topic, metallurgical fundamentals for Foundrymen, is specifically important because it takes us back to the basic, the core principle govern our casting process. We talk about a lot of technologies, anything, but it is basically you need to go back to our basics to understand what it is. That gives us basic of our thing. In foundry industry, metallurgy forms a backbone of quality, productivity, and innovation. And revisiting these basics will help every one of us, whether shop floor engineer, supervisor, or technologist, to strengthen our decision making and improve our results. We are extremely honored to have with us Mr. C. Ravi Chandramouli sir, Managing Director, Quality Technologies Private Limited, our past SR Chairman, an industry expert with decades of hands-on experience in metallurgical systems, quality improvements, and foundry operations. Sir, thank you very much, sir, for accepting our invitation. I think we have been discussing for quite long, and thanks for valuable time, sir. I also extend a warm welcome to our colleagues from Hyderabad chapter, Chairman Sri Raghav Reddy sir and Honorary Secretary Lakshman Rao. This collaborative initiative between both chapters, I hope it will continue together. And I wish all the participants highly informative interactive session. I'm sure that you will be enriched with the knowledge of Mr. Ravi Chandramouli sir, and I'm requesting you to deeply involved and ask questions and understand the subject in detail. Thank you once again for everyone. Let us move forward. We can start today's session. Thank you.
Thank you, Sindhu sir. Actually, how can we can miss actually Chandramouli sir actually to have we need to have a formal introduction of him. Everyone knows him, but still I request actually Hem Professor, a council member, to introduce our speaker for the day to the audience.
Thank you, Raj. It's my honor to introduce today's speaker, Mr. Chandramouli sir. He's a graduated in BTech Metallurgy from IIT Madras in 1977, and further he continued in the same institute to complete MTech in Industrial Metallurgy in 1979. After working in the industry for nearly 5 years, he started an aluminum and magnesium alloy foundry and also registered for a patent for special lightweight alloy that were being supplied by his company to ISRO. Thereafter, his company, Quality Technologies Private Limited, Hyderabad, diversified its activities and presently is one of the largest manufacturer of metallurgical consumables in South India. The company manufactures more than 100 types of products and supplies them to more than 500 customers all over the country, directly from their factory at Hyderabad and also through their warehouses at Coimbatore and Ahmedabad. Mr. Chandramouli sir travels extensively and regularly gives lectures on topics concerning metal casting technology and also on issues concerning to MSME sector. Thank you, sir. Its floor is yours.
Thank you very much, gentlemen from Chennai chapter, Mr. Senthil, Mr. Hari Prasad, and Mr. Majaragan. It's I'm privileged to give you a talk today on fundamentals of metallurgy. See, today what I'm going to do is I'll essentially talk to you about the iron carbon diagram. There are a lot of other subjects before and after this, but since iron carbon diagram is what is very popular and most foundries with whom we're talking have a lot of cast iron and SG iron production going on, I'll share with you some of the fundamentals of iron carbon diagram as related to what we see every day in the microstructures on the shop floor. I'll now switch on to the PowerPoint presentation. So you'll not be able to see my face, but you'll be able to understand the whole thing from beginning. I'll just start off. See, my topic is iron carbon diagram and its application in microstructural analysis. You're able to hear me, gentlemen? Can you all hear
the
me?
screen is not. Yes.
Pardon?
Yes.
Yeah,
Yes,
thank you.
we are all hearing.
Thank you, sir, because I'm not able to see any of you because I'm on the PowerPoint.
So the screen is not visible for us, sir. You can share the screen again, sir.
Okay, sir.
Yeah.
Can you see it now?
No, sir.
One
Not
minute, sir.
visible.
No. Yes? Can you see it
No,
now, sir?
sir.
No, sir. No.
Okay, 1 minute. Please wait. Sorry.
Sir, click on share and your screen in that icon, sir. So entire screen will be shared, sir.
Yeah, 1 minute, sir. Share content. Screen.
Click on share and the screen, sir. Exactly, sir. Screen.
1 minute, sir. Can you see it now, sir?
Shailesh,
Sir, சொல்லுங்க sir. Yes, sir.
matches.
I will call. Wait, sir. Check, sir.
Now you can hear me? And you're able to, now I have to go for share, no? I put share content.
So you can select share entire screen, sir.
Yeah.
Yeah.
Now
Yeah. Now your screen is visible.
I go to, yeah, 1 minute. I'll minimize and go to the PPT. Yes, sir. I opened the minimize. Yeah, now?
Yeah. You can go to presentation mode, sir.
Now when is the presentation mode, right? When is that? Oh, Zoom
Still in normal mode, sir.
When is that?
Yeah, still in normal mode. Presentation mode you can try.
Yeah. No?
No,
Can you
now
see me?
the screen has come out.
Okay, sir.
No, sir.
Sorry, gentlemen. Now join. Okay. இல்ல அது வரல. இருங்க. உங்களுக்கு வந்துட்டா பிரசன்டேஷன்? இருங்க, இப்போ வருது. இருங்க. Okay. Sorry, gentlemen, for the delay. I'll start.
Yeah, now it is okay, sir.
Thank you, sir. So I'm going to give you, in this lecture, I'm going to talk about the ion carbon diagram and its application to microstructural analysis as we see it in the under the microscope. Okay, gentlemen? See, in my lecture, we'll be talking about understanding the concepts at the atomic level. That means what are microstructure which we see, how is it related to the atomic level, at the atom level, crystallographic structure, then influence of various alloying elements, then translation to phase diagrams and microstructures. See, fundamentally what happens is any alloy consists of various elements, and the properties of these elements at the atomic level influence how the alloys are formed. And depending upon how the alloys are formed, they transform into various phase diagrams and various melting points and various percentage additions, etc. And finally, when you cool the metal and break up, study the microstructure, it is a function of these phase diagrams, which in turn is a function of the alloying elements, and which in turn is a function at the atomic level. So fundamentally, the structure of the atom at the structure of the element at the atomic level is what influences the final microstructure. We have, see now, we have metals and non-metals. All elements can be defined as metals and non-metals. And mostly all metals are known as crystals. That means the same pattern is repeated throughout the lattice and matrix. You have various crystal structures. We have what is known as a cubic crystal structure, tetragonal structure, hexagonal structure, orthorhombic structure, monoclinic, triclinic, and trigonal. These are some of the structures which we come across commonly in all the metals that we deal, metals and elements and alloys that we deal with. This is how the various structures look. Crystals. See, ultimately, as I was trying to tell you, all metals are crystallographic in nature. By crystallographic, we mean the same pattern is repeated in a three-dimensional manner. And we have various type of such crystal structures. We have what is known as a simple cubic. What you see on the top here, this is known as a simple cubic, where it just consists of 8 atoms at the 4 corners of the. See, these 8 atoms keep repeating throughout the alloy or the metal, and this is known as a simple cubic. Then you have another structure known as a face-centered cubic. In this, apart from the 8 atoms at the corners, you also have 6 more atoms on all the. As you know, a cube has got 6 faces. So on all the 6 faces, you have another set of atoms. Then we have another structure known as a body-centered cubic. That means apart from the atoms at the corners, you have one more atom in the center. These are all line diagrams of various types of structures, crystal structures which are available, which are present in all elements and metals. Then we have what is known as simple tetragonal. The above 3 are cubic. Tetragonal means one side is longer and other side, it's a square. You can make out from the figure, photo which I have, sketch which I have shown you. Then again you have body-centered tetragonal. Then you have what is known as hexagonal. Graphite is hexagonal basically. Then simple orthorhombic, body-centered orthorhombic, base-centered orthorhombic, face-centered orthorhombic, rhombohedral. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have put 14 such structures. As you go to some of the other higher elements, there are some more structures which are available. So most elements and most metals follow one of these structures. To give you another view of this, I'll show you in the next slide. This is how that. This is how the face of simple cubic looks. Body-centered cubic. Sorry. Okay, the same structure is repeated. See now, you have seen how it is repeated. In the first stage, we just showed you only one atom. In the second line, you'll see how these atoms. See, this is 1/8 of an atom. There are other 8 atoms, so all of them form together. You can see from this is simple cubic, body-centered cubic, and face-centered cubic. In the first set of sketches, we have shown only one atom. Then we have shown the same atom in 3-dimensional. And in the bottommost, you can see how all these atoms repeat themselves. And this is how the final metal or element looks like. The element with, for example, iron has got a simple body-centered cubic at some temperature. At other temperatures, has got face-centered cubic, which I'll explain to you in the next set of slides. So depending upon how the element is structured, this is how the metallic structures look. Any doubt till now, gentlemen? Iron has got three structures. It's called body-centered cubic, then it goes to face-centered cubic, then it goes to body-centered cubic. So iron, as you heat it to various temperatures, it changes its crystallographic structure in various ways. Carbon, since we're talking about iron-carbon diagram, I'm trying to show you how the structures of some of the elements which go into cast irons or SJ irons, how their structure looks. Carbon is known as hexagonally close packed. Silicon is known as face-centered cubic. Manganese has got a body-centered cubic structure. Sulfur has got a rhombic structure. Phosphorus orthorhombic. Nickel is face-centered cubic. Copper is face-centered cubic. Chromium is body-centered cubic. Molybdenum is body-centered cubic. So these are the various elements which we normally deal with in iron-carbon diagram. And here I have tried to explain to you how the various structures look. Now, for you to understand it better, I'll go back to the previous slide. So, like I told you, iron has got both face-centered cubic, then it becomes body-centered cubic, and then again it becomes face-centered cubic. Well, I told you that sulfur has got a monoclinic. So this is simple monoclinic. This is how sulfur looks. Then I told some of the other elements like nickel, chromium, all of them have got FCC structure. That's so manganese has got other structure. So this is how the various elements which go. So all the elements which go into the manufacture of cast irons or which are in the composition of cast irons or SJ irons, there are various elements. Each element has got a different type of crystallographic structure. A crystallographic, since they are all elements basically in nature, it's the interplay of all these various crystals which intermingle with each other, which get mixed with one another, that forms the final alloy which we are talking about. An alloy is nothing but a combination of various elements in various proportions. When various elements mix together to form an alloy, since each element has got a separate structure, separate crystallographic structure, all these elements interact with each other, fit into one another, and then they form the alloy. Now, there are some basic rules for the formation of alloys. These rules are known as Hume-Rothery rules. So now what did we talk about till now? I was trying to tell you, we are talking today about iron-carbon diagram. Iron-carbon diagram, we have various elements, carbon, iron, etc., whatever I've shown you in this slide. And each of them has got a different crystal structure. When you make an alloy, these various crystal structures are melting together or forming together and forming an alloy. But they cannot form an alloy just like that. There are some other rules for the formation of alloys, which I'll show you in the next slide. These rules are known as the Hume-Rothery rules, and these are the fundamental rules on the basis of which various alloys are formed. The atomic radius of the solute and solvent atom must not differ more than 15%. Solute and solvent are solvent is the major element. In the case of iron-carbon diagrams, it will be iron. Solute will be carbon. Solute will be manganese. Solute will be sulfur. Solute will be phosphorus, chromium, etc. So when you're mixing all these atoms together, unless the atomic radius, each element has got a different atomic radius. The radius between both these elements should not differ by more than 15%. So only when the radius is less than 15%, that means only when both the solute and solvent atoms, that means iron and its other element, which are going to, only if the radius of these two atoms is less than 15%, is one of the important factors. If the radius is less than 15%, one fits into the other. If the radius is much more, then the atom with the higher radius will push out the atom from the lower radius, and the alloy formation will be difficult. So one of the fundamental conditions for forming a good alloy is the atomic radius of the solute and solvent atom must not differ by more than 15%. And then the second point, the crystal structure of the solute and solvent must match. If you remember, when a few slides back, I showed you how iron is FCC, BCC, FCC, and again BCC. Similarly, chromium, nickel are all having FCC structure. So that is one of the reasons because the crystal structure of these elements are all almost compatible, that they form a very good alloy. Complete solubility occurs when the solute and solvent have higher valency. 1 minute. Okay, complete solubility occurs when the solvent and solute have the same valency. A metal will dissolve a metal of a higher valency to a greater extent than one with a lower valency. See, in atomics, every atom has got what is known as valency electrons. These are the electrons on the outermost shell. I'll not go very deep into that. Every atom is made up of various electrons, protons, and neutrons. The electrons which are on the outermost shell are known as what is known as valency electrons. So more the valency electrons, then that will dissolve to a greater extent when one with a lower valency, because valency electrons are electrons which attract two elements together or which two atoms together. So this is the reason why when you say complete solubility will occur when the solvent and have the same valency, a metal will dissolve a metal with a higher valency to a greater extent than one with a lower valency. Similarly, the solvent and solvent should have similar electronegativity. If one electron, 1 minute. Solvent and solute and solvent should have similar electronegativity. If the electronegativity difference is too great, the metal will tend to form an intermetallic compound instead of solid solution. You are all aware of intermetallic compounds. For example, cementite, which is there in iron, is an intermetallic carbon compound. Similarly, when you add a high amount of moly or high amount of chromium beyond the solubility, then it forms an intermetallic compound which does not dissolve into the parent alloy. So these are all known as intermetallic compounds. So to again recap, every element has got a crystal structure. Every element forms a crystal, metallic crystal structure. There are various types of crystal structures: body-centered cubic, face-centered cubic, orthorhombic, etc., etc. When you form and all the elements which go into the in iron carbon in the cast irons, namely iron, carbon, sulfur, phosphorus, manganese, nickel, chromium, moly, etc., etc., all of them have got different crystal structures. When these crystal structures, when you form an alloy cast iron or any other iron, since we are forming all these together by melting in a furnace and casting them, depending upon these following rules, which are known as Hume-Rothery rules, these will form good alloys, or they'll form intermetallic compounds, or some of them will come out as phases, etc. When two or more metals are combined in the form of solid, solutions to form alloys. The guiding rules for the formation of solid solutions are known as Hume-Rothery rules. Phases are formed during the course of solidification of the solid solutions. Now what happens is, since each element has got a different structure, each has got a different valency, each has got a different melting point, another point. Depending upon the Hume-Rothery rules which I explained, some of them will form an alloy, some of them may precipitate out as other compounds. So these are the fundamental things. The crystal structure and the Hume-Rothery rules will decide how good an alloy is formed, how homogeneous an alloy is there, or how much intermetallic compounds precipitate out. A phase is defined as a physically distinct and chemically homogeneous portion of a system that has a particular composition and structure. When you take a drill bit, when you take a drilling from a cast iron, you'll get the same composition throughout. Same amount of iron, same amount of carbon, sulfur, phosphorus, etc. That is chemically, it's homogeneous. But microstructurally, it will not be homogeneous, because the crystal structure of each element is different, because the crystals are different. When they form, each phase will, depending upon the temperature at which they homogenize, the temperature at which they mix together, and at the rate at which they solidify, at the rate at which they form various solutions and go, depending upon that, various phases are formed. Phase diagram. See now, how do you understand these phases? For this, we have what are known as phase diagrams. Phase diagrams comprehensively show various phases at different compositions and at different temperatures. See, because each element has got a different melting temperature. Each has got a different crystal structure. And the amount of each element percentage which you are adding is different. Depending upon the element percentage, depending upon its melting point, depending upon the rate of solidification, its crystal structure, depending upon all these, various types of phases are formed. So all these phases, to understand them and study them, we have what are known as phase diagrams. A phase diagram will comprehensively show you various phases at different compositions and at different temperature. For example, carbon in iron and carbon less than 0.2 or 0.3, we'll call it a steel. When it goes to 1.1, 1.2, 1.0, 1.8, we'll call it high carbon steel. When it goes almost beyond 1.8 or so, you call it cast irons. Then you have hypoelectric iron. Then we'll come to that. There are, depending upon the compositions, you have various structures forming and all that, and phases also forming. Now, we have three main types of phase transformations. Periodic transformations, when one liquid and one solid phase change into a new solid phase. Eutectoid, one solid phase changes into two solid phases. And eutectic, when two liquid phases solidify as one single phase. For example, if you take 4.3 carbon, both are liquid, but when they start solidifying, they solidify exactly as one single phase. That is known as eutectic. When you go lower temperature, the same one solid phase changes into two different phases. For example, it changes into ferrite and perlite. So, and periodic is one liquid and one solid phase changing into a new solid phase. So, when you look at a phase diagram, all these types of phase transformations are observed. Now, let us look at the iron carbon diagram. I was talking to you about temperature and composition. See, on the x-axis, 0% carbon, 0.5 carbon, 1%, 2. All of you know this. This is a very, very famous diagram. Finally, it goes up to 6.7 or 6.3, 6.7. And here we have temperature up to 1600 degrees. So, in this phase diagram, what is happening is, if you take pure iron itself, as I showed you, has got two phases, delta iron. I told you, FCC and BCC and FCC. Pure iron itself transforms into various phases depending upon the temperature at which it goes. Then as you start increasing the carbon, then you have peritectic phase. Then you have eutectic phase here. Then you have eutectoid point here. So eutectoid point, what did I tell you? One solid phase going into two solid phases. Ferrite and austenite you have 0.76. You have both ferrite and cementite. So this is how the iron carbon diagram is, and here you have what is known as hypoelectroid. Hypoelectroid means wherever the carbon is less than 0.76, the percentages of iron and steel below that are known as hypoelectroid ions. Then when the carbon percentage is between 0.76 to 2.14, it's called as hyperelectroid. Then you have similarly eutectic point 4.26 carbon. Less than 4.26 carbon is known as hypoelectric, and more than 4.26 is known as hyperelectric. Just as you have hypoelectroid and hyperelectroid, here you also have what is known as hypoelectric and hyperelectric. Here you can see in this phase diagram, this is liquid above 1600. The whole thing is in a liquid form. And as the carbon increases, the entire temperature, solidification temperature is reducing. It comes up to approximately 1148 degrees at 4.26 carbon. The entire alloy will start melting at 1100. If you go to, as you reduce the carbon, the melting temperature is high. That's why you'll find that steels have got a much higher melting point than cast irons, because in cast irons they are operating around 4.3 carbon equivalent. So you have a low melting point. When the carbon is very less, you have a higher melting point. That's the reason you'll find that in steels, the melting temperature and pouring temperatures are high, whereas in cast irons, as you come towards 4.3, the temperature comes down, and again, this entire region is liquid. So this entire region is liquid, and here you have both liquid and austenite. This is what I said, ectoctoid, peritectic. A liquid is changing into a liquid and a solid. If you remember in one of the earlier slides, I said peritectic. Peritectic is one liquid changes into one liquid and solid. So first this liquid is changing into liquid and solid. Then that solid is again changing into solid and solid. It is eutectoid. And finally, you have various phases: ferrite phase, austenite phase, cementite phase, martensite phase. How do all these phases look? I'll show it in the next slide. Austenite is face-centered cubic. See, now please appreciate one thing, gentlemen. Like I told you, all elements have got different crystal structures. And these various crystal structures are being combined to form an alloy through a percentage of addition of various elements. So the final crystal structure of the various phases will be a combination of the basic phases, basic crystal structure of the elements from which it was formed. That's the reason why austenite has got a face-centered cubic, ferrite has got a body-centered cubic, cementite has got an orthorhombic structure, martensite has got what is known as body-centered tetragonal, perlite has got ferrite and cementite, it's called a lamellar form. I'll show you in the next slide. Bainite, another structure, has got ferrite and cementite. Then there's another structure called leduberite, austenite and cementite. So iron carbon diagram is very, very complex. If you want to understand the various phases, if you understand the atomic structure, crystallographic structure of the various elements, if you understand the crystallographic structure of the various elements, if you understand the percentage which is you're adding, and if you understand from that the Hume-Rothery rules, then you understand the phases. Then you'll understand why austenite, ferrite, cementite, martensite, all these have got various crystal structures. So that means the final crystal structure of the various phases is a subset of the phases of elements. Like what we talk in body language, genetics. The genetic structure or the crystal structure of the various phases is totally dependent upon the structure of the elements which have gone into it. Sometime back I showed you where, see, now this is how austenite looks. Has got a face-centered crystal structure of gamma iron. This is how an austenite phase looks. This is how ferrite looks. See, there's a fundamental difference. Ferrite has got a BCC, austenite has got a FCC. If you see austenite, please see this figure is very, very descriptive. You see, in austenite structure, apart from all the 8 corners, you also have a big atom on the face. You have on every face, you have 6. That's why it's called face-centered cubic. Whereas ferrite, the final soft structure which you see in iron, has got a central atom and 8 atoms at the on the various sides. This is a fundamental difference. Austenite, what happens is when you cool it very slowly, it transforms into this. When you cool it very slowly, it transforms into ferrite. Then we have another structure which we all know regularly, which is known as perlite. Perlite is a mixture of 2 phases. Ferrite phase, which is a soft phase, and cementite. Cementite here I have another diagram. It is an intermetallic compound. It's a compound of iron and carbon, more precise intermediate transition. There, I mean, you're not allowing enough time. So it forms, there's too much of carbon in the iron matrix. So it forms a very complex structure like this, and it is called orthorhombic structure. So now, depending upon the temperature at which you are cooling the austenite or the molten metal, you have ferrite phases. Then depending again upon the composition, that is again, there's what is known as the liver rule. As per the liver rule, depending upon the composition, it will take various phases. So perlite is a mixture of cementite and ferrite. Perlite is a type of microstructure of steel having 2 layered phases. This is how, see, if you see under microscope, you'll have perlite like this. See, this is how you see it. But then if you want to see it in a schematic manner, you have cementite, you have alpha iron, you have again iron, you have cementite, you have alpha iron. So this is a very, very fine structure. Then you have another structure, bainite. Then you have martensite. Martensite is again tetragonal. See, the normal phases which you all encounter on a day-to-day basis are austenite. I showed you how the structure looks. Ferrite, how this looks. Perlite, martensite, orthorhombic. It's not cubic like this, it's orthorhombic. And you have cementite, which is an orthorhombic unit containing formula for 3 iron atoms and 1 carbon atom. So this is how, see, you see 3 iron atoms, 1 carbon atom, 3 iron atoms, 1 carbon atom, 3 iron atoms, 1 carbon atom. All of them form an intermetallic interconnected phase. And this phase forms between various ferrite phases. See, now what is happening is, please, I mean, I'm able to visualize it. See, you have 3 iron atoms. These 3 iron atoms, you have here one iron in ferrite. So it's a combination of the carbon is interspersed between both, and depending upon the cooling, you have cementite formation, you have these various alloy formation. Then we have 2 more stages, but this is mainly in steel. It is not there in what do you say, cast irons that much. Bainite and lower bainite are not there in cast irons. It is mainly in steels. It is a type of cooled martensite. If it cools at a lower temperature, martensite forms when the cast iron or steel is so cooled very fast. When it cools very fast, what happens is the excess carbon does not have time to come out. So it gets solidified in between. In the process, it forms a very hard microstructure. In the case of bainite and lower bainite, these are the structures which are formed intermediate temperatures. I mean, it will be beyond the scope of our present discussion if we have to go into that. But what I'm trying to do in this lecture is just fundamentally to try to tell you what are the various phases and how they interact and what is it. Next speaker. Now, a microstructure. Let us say you have ferrite. If you look at the grain structure under a microscope, this may be ferrite. This is one type of grain. This is another type of each grain. Please remember, gentlemen, when you look at a microstructure, you have known what are known as grain boundaries and various grains. Each grain is a separate crystal. Each grain is a separate crystal. So that means if you look at microstructure and you find ferrite, that entire ferrite, that entire grain of ferrite will be having a structure like this without any dislocations, without any disjoints or anything. That will be entirely one structure. Each grain is a separate structure. So if you are able to see an individual grain under an electron microscope or a scanning electron microscope, you will find that all atoms in that grain are arranged in one particular orientation. If you go to the next grain, they may be arranged in another orientation. See, now here I showed you 3 grains. This entire grain is arranged in one structure. This is another structure. Then you have what is known as a grain boundary. This grain, you see here, I have showed you here, no? The same thing. This is a grain and this is a grain boundary. This grain boundary will have a combination of both these. For example, you have some ferrite, you will have some extraneous elements such as carbon or other things forming the grain boundary, perlitic grain boundary, and all these are grain boundaries. Now, iron carbon diagram, various elements, each element having a different crystal structure. And in order for all these elements to form an alloy, the influence of Hume-Rothery rules, they form an alloy based on Hume-Rothery rules on the basis of their valency, composition, grain size, atomic size, etc. And depending upon the composition and temperature, various phases are formed. And various phases, when they solidify, they again come out as various the transition like ferrite, perlite, various, and each of them has got a different structure. One more thing which influences alloy, carbon and silicon promote graphite formation. Effect of various, see there's one more, see we have the interplay of 2 or 3 elements has got various complexities and various factors emerge. Carbon and silicon promote the formation of graphite. So that's why you have what is known as a carbon equivalent. If you have less carbon and more silicon, it's as good as having low carbon, more silicon, more carbon and less silicon also. Of course, the effect of each element will take. That's why we say carbon plus silicon by 3. That means 3.3 units of silicon will give the same graphite as 1% of carbon. Nickel, copper, and manganese are austenite stabilizers. That means if an alloy has got more nickel or more copper or manganese, it promotes the formation of austenite. Austenite is very stable. That's why you have, when you add more nickel, austenite does not have high thermal expansion. That's why when you add nickel, the thermal expansion of the ions and all, they are very stable, and copper also has the same effect. Manganese also has got the same effect. Chromium, vanadium, and tungsten are carbide stabilizers. Carbide means you have cementite, Fe3C, what I showed you in the, just for the sake of, let me say, clarity, I'll go back to the previous slide. This is cementite. This is a cementite structure. This is a ferrite structure. This is austenite structure. This is a martensite, perlite structure, martensite structure. So each of these structures, each is again a outcome of the parent crystallographic structure of the elements. And again, it's all this. And then again, the interplay of other set of elements. So chromium, vanadium, and tungsten are carbide stabilizers. Carbide means Fe3 is known as cementite. It's also known as iron carbide. They are all carbide stabilizers. So that means in a cast iron, you're having carbon and silicon. The silicon will promote the formation of graphite. The nickel, copper, and manganese will promote the formation of austenite. Chromium, vanadium, and tungsten promote the formation of carbides. So depending upon the final and each of these has got a different property. Graphite has got a tendency to damp the structure. Why we are machine tools made out with grey cast iron? Because it absorbs the vibrations. Nickel, copper, and manganese have thermal stability, maintaining uniform dimensional stability. Chromium or carbide, they give high hardness. So depending upon the final properties of the alloy, you are changing the carbon percentage, you are changing the silicon percentage, nickel, copper, manganese, chromium, vanadium, etc., etc. So each element is added into cast iron for a different purpose. So here we are trying to explain to you the fundamentals on the basis of which the properties can be achieved by adding various things. To give you a simple analogy, you add various spices in your food depending upon the taste you want. Similarly, depending upon the final properties that we want, we add various elements and make the various alloys and get the various properties. See now, in one of earlier showed, I told you, ferrite. This is ferrite. Depending on when it's, I'm trying to show you here how the composition plays an important role. You take an alloy with only 0.4% carbon, you have a different structure. You are totally everywhere for alpha. This is alpha iron, perlite. This is again you have this is all ferrite and you have perlite here. Now when you go to 1.2, because there is more carbon in the alloy, you will have cementite at the you will have ferrite, I mean cementite at the grain boundaries, whereas here you are having ferrite at the grain boundaries. Please note that here we are having perlite. Here also we are having perlite. Now, because the carbon percentage is less, the balance iron is precipitating out as ferrite at the grain boundaries. Ferrite has got very low iron. But when the carbon percentage is higher, after the perlite is formed, the excess carbon is joining with the iron and forming cementite at the grain boundaries. So depending upon how the percentage changes, the microstructure changes, and hence the properties also change. Now, this is how austenitic structure looks under a microscope. Ferrite looks like this. And if you see the hardness of ferrite, no hardness, it will be very, very soft. Cementite. All this area is cementite. This what you see is white. White is all cemented. This is all perlite. All very hard. Fe3C. Perlite. Fine structure. The black is cementite, and then you have in between you have ferrite, cementite, ferrite, cementite. This is another bayanite, which I told another type of microstructure. Martensite. So these are various structures which we have. Ledubrite. So this is how ledubrite structure looks. These are various structures. Martensite. Bayanite. I'm sorry. Perlite. Cementite. Ferrite. Austenite. So here I showed you how the microstructures look. I had also showed you in an earlier slide how they 1 minute. Yeah. So in those I have showed you how the microstructure looks. At the atomic level, this is how it looks. You have seen how austenite structure looks. But this is how atomic level austenite is a crystallographic structure like this. Ferrite has got this structure you have seen. So here, while here I'm trying to show you what are the structures on the basis of which various phases are present. And there I have showed you actually when you look at it at a microscope, you will not see these. You kindly have a look at this. I'll again take you back to those. At the subatomic level, at the atomic level, this is how austenite, ferrite, perlite, cementite, let all this look. But when you look at a microscope at 100 or 150 or 200 magnification, the way it looks is totally different, which I'm showing you right now. Austenite looks like this. Ferrite looks like this. Cementite, perlite, bayanite, and martensite, and ledubrite. So these are the various structures. How they look. Just excuse me. నేను జూమ్ మీటింగ్ లో ఉన్నాను మళ్ళీ ఫోన్ చేస్తాను. Sorry. So I'll run through the whole presentation once more. It's easy for me to say this because because I'm presenting it and it's 1 minute. In my lecture, I've been trying to explain to you all ion carbon diagram, its applications, and microstructural analysis. We are now trying to understand the concepts at atomic level. Then I have discussed about alloying parameters, microstructures, influence of various elements. First, I'm going to talk the concepts at atomic level. We talked about each element, all elements are metal crystals, cubic structure, tetragonal, hexagonal. These are various types of structures. And these are the various types of structures which I already showed you. Simple. These three form the cubic structures, tetragonal structures, orthorhombic structures. If you see once more, these three are cubic structures. In cubic itself, you have 3 varieties. In simple tetragonal, you have 3 varieties. And then orthorhombic, you have 4 varieties. Rhomboidal, monoclinic, and there are many more structures. In fact, there are roughly around 70 to 80 structures. But for the sake of our discussion, these are the common structures which appear in most elements, which we come across every day in our foundries. And these are the structure. Look, this will be how a single atom look, simple cubic. But when various atoms are joined together, this is how the entire element will look. This is how the entire element will look in a body center, face center. These are the basic metals. Again, when they form various alloys, you now we will appreciate various color atoms coming together and mixing together and melting and forming phases. You will have various phases of iron, carbon, etc., forming those structures. Then iron, carbon, These are the various structures of iron, carbon, silicon, all the items which go into our regular elements. I mean, cast irons. Then fundamental, this is the most important. The Hume-Rothery rules, which form the foundation for any alloy to be formed. They should be almost same size, radius. Structure should match. Then solubility will occur, have higher valencies, and similar electronegativity. That's why you'll find that not all elements can be formed into alloys. There are some of them which form as intermetallic elements or will just stay outside. Now there's one thing as solubility occurs. Now anything has got a limit to solubility. If you add too much of chromium, let us say you add too much of salt to water, after some time the salt will remain as salt. Similarly, if you add too much of nickel or chromium, of some sense the nickel will remain as intermetallic compound itself. When you go to very high alloys, when you add chromium, very high chromium or very high nickel and all the nitrosilal and all that, they don't form an alloy. They just form as a separate element. You take NiHADs. Why when the nickel is very high, what happens is it forms an intermetallic compound, and that's where cracking and other things happen, or when you heat treat it. Then these are the bases on which the phase diagrams are formed. Solidification, then new crystal structures are formed. Peritectic, these are the three types: peritectic, eutectoid, eutectic. Just as you have various, you have in our own IIF, we have student member, company member, like that, Here also have various types of phases and formations. And in the iron carbon diagram, you have total liquid here, you have liquid plus solid, then you have liquid plus solid, then you have austenite here, which is again eutectic. Then you have various, depending upon various temperatures, various percentages, the iron percentage, carbon percentage. You have here, this is 100% iron. As you go this side, it will be 100% carbon. Depending upon how much percentage of carbon, this is how the phase diagram looks. And this is the most important part of the phase diagram. Actually, what happens, Mr. Chairman Senthil sir, some of these physically sitting in front of the people and telling will be easier to explain, because I somehow find that some of this is very difficult to explain on a Zoom, but still whatever I can do, I'm going to do the best, because when you interact personally, you can draw a lot of experiments and other things. Next. Austenitic phase, ferrite phase, cementite phase, martensite. These are the various phases. Then next I showed you how the phases look. How austenite phase looks, these phases look. Then how each grain is a different crystal, and whatever does not form into the crystal precipitates out and forms a grain boundary here. Carbon and silicon form out a graphite formation. Nickel, copper, manganese, austenite stabilizers. Carbide stabilizers. And this is a main phase. It forms a grain boundary of ferrite. It forms a grain boundary of cementite, because here the carbon is more. Thank you very much. Sir? Hello?
Hello, sir.
Sir, my presentation is over, Reddy garu.
Thank you. And all are very concentrated and leanamaipoyaru, sir. మీ యొక్క ఎవరు మాట్లాడట్లేదు చూడండి.
No, I don't know if the people understood me or not. My worry is that.
Yes, absolutely. These are all it coming out memory of my college days.
Sir?
Yeah.
PowerPoint was very good, sir.
Thank you, sir.
It explained more.
Excellent.
Sir. Yes.
Can I close the
You explain
PowerPoint
like
and come back to the... Can I close the PowerPoint, gentlemen?
Yes.
Yes, sir.
Thank you,
Ravi
sir.
Chandramouli garu.
Yes, sir.
Ravi garu.
Yeah.
Your presentation is excellent, and your slides are very good. All are basic fundamentals. and it reminded us, it is our college day. Our
Yeah.
professor used to teach like you. So you have told us, FCC, BCC, simple cubic, and
Yes, sir.
different structures, phases, and then iron carbon equilibrium diagram and metallurgy. And see, maybe in the next lecture, what you can cover, what is the effect of each element for in alloy? So
Hey, I
that
can
is
do
a
it
more,
totally, yes, sir. No problem.
That would be appropriate. Correct.
yeah. Yeah. And what are the new alloys developed recently, and what is the function of each element, and how the alloys are made? So these things very useful for a foundryman. But today you gave a basic and important lecture, and I just really got all my college days memories. Where I went to the
You,
NIT branch, National Institute of
thank you very much, sir. Thank
Refined,
you, sir.
yes. Yeah. And thank you very much for your time and efforts in spite of your traveling from Pune yesterday overnight. And again, you have taken this pain and given a lecture. Thank you very much on behalf of Chennai chapter and also on behalf of Hyderabad chapter. We are all thankful to you. And also we thank Chennai chapter people for organizing and coordinating this. Also special thanks to our Dinesh sir, who is coordinating for all software things and presentations, and all the finally we thank you very much for all participants. Almost more than 40 people are present, and we look forward to see you again
70.
with such lectures. 70 people have come.
70. Yeah.
70, yes sir, yes, thank you, correction, 70.
Thank you, sir.
Thank you very
May I
much. Sir.
close?
Thank you.
Any questions? Any questions, sir? Or can I close?
Audience, I think they will write mail or SMS to you, sir. Any questions? I think,
Okay, sir.
okay?
Thank you very much, gentlemen. Thank
Okay,
you, sir.
thank you, sir.
Thank you.